Hello everyone, I'm Basu Panthi. I'll be teaching chemistry 23 or organic chemistry 1. Let's start another lecture on chapter 3, functional groups, intermolecular forces, and so on. Let me share the screen. You can see it. Let's do the slideshow. Introduction to organic molecules and functional groups. When you look first 2 chapters, you might think what class I'm taking. It does not look like organic. Now we are going to start the organic molecules, functional groups, and so on. So functional group. In organic chemistry, a functional group is an atom or group of atoms with characteristic chemical and physical properties. Certain groups have certain properties. There are many molecules with similar group. Like in the periodic table, we study the groups, everything is similar. It's just the identifying similar properties and so on. So mostly organic molecules are the carbon compounds, or we define hydrocarbons. So carbon and hydrogen are called basic elements or fundamental elements. Anything other than carbon and hydrogen are called heteroatoms. Carbon and hydrogen are fundamental. Anything else is hetero. Okay. We'll see all the different kinds of bonds and so on. The functional group. Distinguish one organic molecule from the another one. You'll have the long backbone, similar hydrocarbon, but at the end, that group is different. That's the identifying group or characteristic group. That's called functional group. It will determine the geometry, physical properties, reactivity, and so on the molecule. Okay. So reactivity, heteroatoms and bonds confer reactivity on a particular molecule. Heteroatoms have lone pair of electrons, or they have electron deficient sites, or many things. A bond that makes a molecule a base and a nucleophile easily broken in chemical reactions. So what I mean, what does this mean here? If you have something carbon and heteroatom, there should be some sort of charge separation, plus minus. That creates the reactive sites. You know, here pi bond is easily broken, so it's reactive. But if you have carbon-carbon, it's not reactive because there is no any reactive sites. That's what it means. So functional group, anything what identifies. So here we don't have any functional group, it's just the hydrocarbon. Here OH, that's the functional group. We call alcohol. So the first molecule has only carbon-carbon or carbon-hydrogen bond. That means no reactive side, so it's simply unreactive or less reactive. But the other one, OH, it's called alcohol. It has different property, reactive sites. So other molecules with the OH group are called alcohols too. They have similar reactivity. So for example, if you have CH3OH, 1 carbon, and C2S5OH2 carbon, C3H7OH, C4H9OH. So going big, you know, the size is bigger, but still the OH functional group, they have the similar properties, everything. That's what the functional group means. So let's start. Hydrocarbons. Compounds only containing hydrogen and carbon are called hydrocarbons. Alkane. Just the carbon and hydrogen, they are bonded by single bond. We'll talk about this in coming chapters. Alkene, at least 1 carbon-carbon double bond. Alkyne, at least 1 carbon-carbon triple bond. If you have alternate single double bond and it's in the ring, that's called aromatic compound. Slowly you will get familiar with these compounds, okay? So alkanes, alkenes, and alkynes. Aromatic, alternate single double bond. They have characteristic smell, everything. But for organic chemistry one, we don't talk a lot about aromatic compounds. They should be part of organic too. With the hetero atom, Z can be carbon, nitrogen, I'm sorry, oxygen, nitrogen, or so on. That's the heteroatom other than carbon. Let's look some example. Alkyl halide, any halogens, we'll talk about alkyl halide in detail. One halogen is connected to the carbon, alkyl halide. OH group is connected to the carbon, that's hydroxy group, alcohol. If the oxygen is between two carbons, that's ether. So all these first three functional groups, we'll talk detail in coming chapters. Amine, if you have one nitrogen, that's called amine. There are primary, secondary, and tertiary. So you have RNH2, R2NH, and R3. Instead of oxygen, if you have sulfur, that's called thiol and sulfide, similar to alcohol and ether. And another one, when carbon is bonded with oxygen by double bond, that's called carbonyl group. There are many functional groups with the carbonyl group. So what they are? Let's look. Aldehyde. If one side is alkyl group and other side is hydrogen, that's called aldehyde. If both sides we have some alkyl group, not the hydrogen, that's called ketone. If you have hydroxy group one side OH and other side alkyl group, that's carboxylic acid. If one side we call alkoxy, oxygen, then alkyl group, other side alkyl group, that's ester. If one side of the carbonyl group amine or nitrogen, that's called amide. See the difference between amine and amide. Amide, the nitrogen is next to carbonyl. And acid chloride if the halogen is next to carbonyl. So these are another functional groups. The question, do we need to know all these functional groups? The answer is yes, but not in the first quiz or exam. Slowly, by the exam, you will know or get familiarized with the main common functional groups. A functional group determines all of the following properties of a molecule: bonding and shape, type and strength of intermolecular forces, physical properties, nomenclature, chemical reactivity. We have a special way to name organic compounds, that's called nomenclature. You will see many things in chapter 4, and after chapter 4, everything will be complete in organic chemistry. Then we go that way, okay? Because we don't know naming and all the skeleton and many things. Because, or the homologous series, 1 carbon, 2 carbon, 3 carbon, 4 carbon, same functional group with different carbon numbers, that's called the homologous series. Talk about that one and how to name it, okay? So first thing, let's talk about intermolecular forces. What is intermolecular forces? The name is enough. Forces between two molecules. When you drink water, what do you drink? H2O. How many H2O? Many. That's okay. But how they are connected together? Water molecule is HO. Yes, right? But we don't drink that one. These are covalent bonds. How this molecule bonds with the other water molecules or how they come together? That's the intermolecular forces. That's what we are talking. Okay, we'll talk in detail. And functional groups determine the type and strength of this interaction. Ionic and covalent compounds have very different intermolecular interactions. One time I was asking to my student, how many types of bond you know? Oh, ionic, covalent, hydrogen bond. Hydrogen bond is the intermolecular forces. It's not the real bond. Let's see what it is. So ion-ion interaction. In ionic compounds, The ions, they attract each other, the ionic interaction keeps them together, and they are even big molecule, in the lattice. But intermolecular forces in covalent molecule, they are not charged. What are they? There are three types of intermolecular forces. Make sure you know the name as well as what kind of molecule have this kind of force. That's very important. These things are important. Okay. Van der Waals, sometimes we call London force or dispersion force as well. Dipole-dipole interaction and hydrogen bonding. All of them are intermolecular forces. So Van der Waals force are also known as London forces, or sometimes we call dispersion force. They are very weak. Every molecule has the Van der Waals force. They are very weak. Okay. They are present in non-polar molecules or any kind of molecules. So how that happens? For example, CS4 has no net dipole. How can it has Van der Waals force? At some point when they are, rotating, vibrating, or at some point somehow it creates temporary dipole, right, in the molecule. And that temporary dipole causes the other molecule to create the dipole, and that's why it helps. But that's the temporary dipole. Any molecule can have Van der Waals interaction. If you have nothing, then it has Van der Waals force. So all compounds exhibit Van der Waals force. The larger the surface area of a molecule, the larger the attractive force between two molecules, and the stronger the intermolecular force. If the intermolecular force is stronger, then the melting point, boiling point, everything will be higher. If we are talking the longer molecules, have a strong intermolecular force. If shorter, is smaller, by compact, right? So polarizability is a measure of how the electron cloud around an atom responds to changes in its electronic environment. Larger atoms have more loosely held valence electron, are more polarizable. And compounds with large polarizable atoms have stronger intermolecular force. So polarizability, if the molecule is polarizable, that means it has a stronger Van der Waals. Smaller molecule are less polarizable. For example, here, this one, acetone. Okay. So we'll talk about the melting point, boiling point, everything. So branching decreases the intermolecular forces because it decreases the surface area and so on. Okay. So dipole, if the molecule has permanent dipole or it has some sort of polar bond, that is dipole. When you have the heteroatom there, then it has the permanent dipole. But keep in mind, if it has dipole interaction, it still has Van der Waals, so it's stronger. Van der Waals plus dipole. And hydrogen bonding. Hydrogen bonding is the special and strongest intermolecular forces in covalent molecules. If the hydrogen is directly bonded with oxygen, nitrogen, or fluorine, only three atoms: oxygen, nitrogen, or fluorine. Oxygen, nitrogen, or fluorine directly bonded, that hydrogen is very positive, electropositive, and can be attracted with either oxygen, nitrogen, or fluorine. That's called hydrogen bonding. Hydrogen bonding is the strongest of three types of intermolecular forces. So here water, this is the hydrogen bonding. But this one is the covalent bond. This is the covalent bond, hydrogen bonding. It's just the physical force of attraction. These are a few examples. What kind of molecule has what. Van der Waals force can be in anything, all kind of molecules. Dipole only in molecules which have polar bonds. Hydrogen bonding only when hydrogen is bonded directly to oxygen, nitrogen, and fluorine. Ion in all ionic. That's the summary. So physical property. Boiling point. What is the boiling point? Boiling point of a compound is the temperature at which the molecule or liquid molecules are converted to gas. Boiling, we need to supply the energy which is able to break that intermolecular forces so the molecules are apart. How do we distinguish? How do we compare? What happens? What is the trend of the boiling point? Increasing intermolecular forces increases boiling point. So simple. Compounds with Van der Waals force have lower boiling point. Compounds with hydrogen bonding have higher boiling point. So I will see the questions. You will see some molecules and ask you arrange them increasing or decreasing boiling point. Look at their intermolecular forces, compare it, and arrange them. So, write this one. So first one has only Van der Waals force. Second one has dipole and Van der Waals force. Last one has all kind of force, so that has higher boiling point. See, this hydrogen is not directly bonded to oxygen, so there is no hydrogen bonding, only the dipole. So larger the surface area, higher the melting point. Here we are talking the bigger molecule, smaller molecule. If you know bigger ions, larger molecule, that's polarizable, higher boiling point. The surface area. So one thing it's not written here, branching decreases the boiling point. Remember that one. Branching decreases the boiling point because it decreases the surface area. So for example, 1, 2, 3, 4, 5, 2, 4, 6, 5, 3, 4, 5, only 4. I just boiling. Next one. Yeah, even they are the isomers. I just boiling. So branching decreases the boiling point. Please remember this one. You need this one in many places. And also the surface area, bigger molecule, and also the polarizability. Melting point is the temperature at which a solid is converted to its liquid state. It's similar to the boiling point. So in melting, energy is needed to overcome the attractive force in the more ordered crystalline solid. The stronger the intermolecular forces, the higher the melting point. It's similar to the boiling point, but there is one difference. Given the same functional group, the more symmetrical the compound, the higher the melting point. Because symmetrical, just think about this one. Symmetrical is kind of spherical. Okay? So we can pack like the symmetrical circles very well inside. So they have higher or stronger melting point, not for the boiling point. So for compounds, it's similar trend with the Van der Waals force, dipole, and hydrogen bonding, it increases. Only the difference in melting point. Neopentane has a much higher melting point than isopentane because this one is more spherical or symmetrical, higher point. And this one, lower melting point. But let me talk this one a little bit. So what I have here. So how many pentane, right? 1, 2, 3, 4. 1, 2, 3, 4, 5. We have 3 isomers, 4 here. One is there. One 2, 3. When we are talking the boiling point, 1 as the highest boiling point, then 2, then 3. Because branching decreases the boiling point. When you are talking the melting point, 3 is the highest. After that, no more symmetrical, then 1, then 2. I told the students, please remember this example one more time. Boiling point, branching decreases, 1 is higher, then 2, then 3. Melting point 3 is the highest because that's spherical or symmetrical. Then 1 because it's the longest, then 2. Only symmetrical effects, otherwise it follows the same trend is in boiling point. Please remember this slide or this example, 1, 2, 3 or 3, 1, 2. What you are talking, melting point or boiling point. Symmetry increases the melting point. That's very important. You will see very often. And most of the time, you will see the molecules and ask you to arrange melting point or arrange them in order of increasing or decreasing melting or boiling points. Just follow it. Read it. Okay? Very important, this one. Solubility. The simple rule is like dissolves like. Ionic compounds are soluble in polar solvent. Covalent molecular solids are in non-polar solvents. When you dissolve the ionic compound, they dissolve, they break into ions. The molecules, they break only the smaller molecules. Okay. So ionic compounds, they break into ions, and maybe you know the solvolysis. The ions will be solvated by the positive or negative end of the solvents. Okay. So butane is the non-polar molecule, soluble in non-polar solvent, insoluble in polar solvent or what? Acetone is soluble in non-polar solvent because this is our organic solvent. This is kind of non-polar. Also, it's soluble in water because this is polar. Sometimes, the polar organic molecules are soluble in organic solvent, but if they have more than 5 carbons, they are not soluble. If anything can form the hydrogen bonding, of course, they are soluble in water. So here, water, alcohol, ethanol, it can form hydrogen bonding, so that looks like it's soluble in water, right? For the cholesterol, it also have the OH group, but this has too many, or the bigger side, which is non-polar. Hydrophilic is water-loving or polar. Hydrophobic is non-polar. So this is hydrophobic part. So overall, the other side is so big, too many carbons, it is not soluble. So in general, if the molecule is polar and contains less than 5 carbons, it is soluble in water. More than 5 carbons, it is not, but sometimes there are some exceptions. You will see immediately here. So there are 2 groups, hydrophobic and hydrophilic. Non-polar, hydrophobic, polar, hydrophilic. So that depends the solubility. Look this table by yourself. So for example, the vitamins, there are many. Some are soluble in oil or water, some are water soluble, some are water insoluble. So vitamin C, how many carbons? 1, 2, 3, 4, 5, 6, right? 6 carbons. 1, 2, 3, 4, 5. 1. How I explain this one? 1, 2, 3, 4, 5, 6 carbon. But our rule is, if anything more than 5 carbon, it will be insoluble. But here there are too many polar ints, too many polar hydroxy groups and oxygen. So this is soluble in water. There are exceptions. Just make a judgment based on the structure. Sometimes they are even bigger molecule are soluble in water. So this is water soluble. Soap structure, we don't need to go more detail, but the soap is kind of, soap has two ends. One is polar end. It's called like this one, the polar sodium salt end. Another one, non-polar tail. When you dissolve in water, this side interacts with the water outside and the tail goes inside. So it forms like a ball or micelle. When you are cleaning, the oil or grease will be trapped inside here and the water swipes up the micelle. That's how it cleans. Okay. So there are many ionophores or bigger molecules. They have different purpose, but we don't go more detail about it. Like crown ethers, depending on the number of oxygen and carbon, that's how they are categorized. If they have 18 molecules in the ring and 6 oxygen, that's called 18 crown 6 or 14, 16, based on the name, and they will be utilized mostly to transport the cations and so on. So, but don't worry too much. The functional group, electrophile, nucleophiles. I think you know from a chapter, if it is electron rich, that's called nucleophile or rich in electron. Sorry, if it's rich in electron, that's called nucleophile. Or if it has lone pair of electrons, that's nucleophile. If it's deficient on electron, or it's looking for electron, or it has partial positive charge, that's called electrophile. And the reaction is between always electrophile, nucleophile, or acid and base. Okay. If you have double triple bond, they are easy to break, so they are more reactive. The reaction is always from nucleophile to electrophile, and don't confuse to put the arrow always from electron rich to electron deficient, not the other way, always this side, nucleophile, electrophile. Biomolecules, there are big biomolecules, everything. We didn't cover this chapter, maybe in biochemistry, like simple sugars, amino acids, lipids, nucleic acids, they are biomolecules. Don't worry, all those. But mainly from this chapter, intermolecular forces and the trends, solubility, so on, and functional group. Okay, that's the simple concept. Not that difficult. And this chapter is combined with the previous chapter, so that will make one quiz or homework. Good luck for everything. Make sure you understand. You make good note. You draw some examples, solve some problems from the book. You should be good to go. Good luck. Thank you.